Thank you so much for coming. My name is Marcello Pavan from Triumph. I'm very pleased to welcome you to this evening's public lecture put on by Science World and Triumph. This is the kickoff lecture for the Physics at LHC, Physics at the Large Hadron Collider Conference, which will be taking place next week on the campus of UBC, organized by Triumph. We have top particle physics scientists from all over the world here this week, and some of them are here today. And we have the grandpapa of all the particle physicists, the Director General of CERN, Rolf Hoyer, who we are delighted to have here this evening. Thank you so much for taking the time off from a beautiful sunny June day in Vancouver, which those are words you do not often hear together in one sentence. And so we're delighted that you're here and welcoming you to this fantastic space. And on behalf of Science World, on behalf of Triumph, I'd like to welcome our partners in this venture, Pauline Finn for Science World.
Thank you, Marcello. We're just thrilled to have everyone here. And welcome to our rejuvenated and expanded facility. It's been 2 years of renovations, and we're thrilled to invite the community back to our fantastic facility. We are honored tonight to partner with Triumph to bring Dr. Hoyer here. One of our goals is to expand and be more relevant to teens and adults. And taking a look at the audience tonight, I think we're setting the bar for those future endeavors. Before we get on with the main event, I would also like to invite you all to consider coming back to see our summer feature exhibition, Da Vinci the Genius. So take a look around on your way out tonight. There's lots more to see in terms of our other galleries. And without much further ado, I would like to pass it back to Marcello to get on with our proceedings this evening. Thank you very much.
So as I said, this is the kickoff event for the Physics at the Large Hadron Collider Conference. It's bringing together all the particle physicists from that large experiment in Geneva. They're all going to come here next week to talk about the latest events. It's going to be an extremely exciting and important conference. And to welcome you, I'd like to invite Dr. Rob McPherson at Triumph and UVic, who is the conference chair for the PLLHC conference, to come up and say a few words.
Good evening. Scientific research enriches the world not only through direct technological development, but also by fostering strong international collaboration amongst disparate nations. Fundamental scientific research enjoys the luxury of addressing the basic questions of our universe using experimental methods and mathematical theories which cross cultural and political boundaries. What are we made of? Where did the universe come from? What is the fate of the cosmos? Particle physics, the investigation of some of these most fundamental issues, has nearly a century-long history of advancing knowledge and promoting international cooperation. Rolf Hoyer has been a leader in particle physics for 3 decades, and in 2009 became the Director General of what is now perhaps the world's foremost scientific laboratory, CERN, in Geneva, Switzerland. Rolf completed his studies in his native Germany, performing experiments at the DAISY laboratory in Hamburg before moving to CERN. He quickly assumed leadership in the construction of the huge central detector of the Opal experiment at CERN, the Large Electron Positron Collider, one of the most successful science projects in history. By 1994, after supervising the initial operation of Opal, he became the overall collaboration leader. In 1998, he returned to DAISY and became research director of the laboratory. And in 2004, as research director, he faced and addressed some serious technical challenges in the operation of their flagship project. In 2009, he returned to CERN as Director General, effectively the CEO of one of the largest scientific organizations in history. Rolf Hoyer has a long history of collaboration with Canadians, especially many of us at BC universities and the Triumph Laboratory. In Rolf's tenure at DAISY, he was instrumental in bringing together the international community in the development of the next generation of particle accelerator technology, which is relevant to both particle physics and wider society. This technology is the basis of the linear accelerator project at Triumph today. Also, at this time, the ATLAS experiment at CERN is one of the largest scientific projects in Canada. The 200-person-strong Canadian ATLAS group is one of the largest scientific collaborations in Canadian history, including the 3 leading BC research universities and Triumph, which hosts one of the principal international LHC computing and analysis centers. We're all very pleased to have Rolf back in Vancouver, opening the Physics at the LHC conference tomorrow on the UBC campus, hosted by Triumph, UVic, UBC, and SFU. And we're looking very much forward to his lecture this evening, Unveiling the Universe. Rolf.
Okay, we are starting now with a film.
Everything started at the moment of the Big Bang, 13.7 billion years ago. Time and space begin when a tiny point full of energy starts expanding at an incredible rate. An unimaginable amount of energy transforms into matter and antimatter. But shortly after, all antimatter has disappeared, and only a tiny fraction of matter is left, still enough for all stars and planets in our universe. In the first 3 minutes, protons and neutrons form the lightest nuclei, while the universe continues to expand and to cool down. But it takes almost 400,000 years until hydrogen and helium atoms can form. Now the universe has become transparent. Light from this era can still be seen today as the cosmic background radiation. Gravity begins to pull the hydrogen and helium together. Stars are born. Fusion inside the stars forms heavy nuclei, the base of life. And these building blocks are thrown into space when stars die in giant explosions. After 9 billion years, gravity pulls some of these remnants together to form our solar system with our planet Earth, where evolution gives rise to life, intelligence, and consciousness. Since its awakening, humankind has wondered about its origin, and today we have developed the tools to give answers. Scientists from more than 100 nations are working at CERN on the Large Hadron Collider, the most powerful tool to study the first moments of the universe. The LHC is a circular machine of 27 kilometers circumference that accelerates beams of protons to more than 99.99% of the speed of light. And collides them in 4 interaction points. 4 huge detectors takes snapshots of each collision, up to 600 million per second. In these collisions, energy is transformed into particles, just like in the first fraction of a second after the Big Bang. The study of these data will soon allow us to answer some of the big questions. Will we find the reason why antimatter and matter did not destroy each other completely? Will we understand the primordial state of matter before protons and neutrons formed? Will we find the particles that make up the mysterious dark matter? Will we find the Higgs particle that is responsible for giving mass to all particles? The LHC will bring us closer to an understanding of our universe.
Yeah, good evening, everybody. If my voice is a little bit strange, I was just falling out of the plane, so I'm not fully awake. Okay, but I make myself awake during the talk. Okay, unveiling the universe, and you see here, we are here in this very nice dome, here, which is an icon. And you see we have something together. CERN also has an icon like this. Ours is out of wood. And we also have events inside this dome. And since not everybody of you knows what CERN is or what CERN is doing, I just have one transparency concerning CERN. What is our mission? Our mission is fourfold. Research, that's the raison d'etre why CERN was founded. You cannot do research without innovation. You cannot do it without education and training. And one specialty of CERN is you cannot do it alone. Yeah? You unite people from different cultures and nations because science is a universal language. And this is fantastic. So, what do we want to do in the research? We want to push forward the frontiers of knowledge. We want to unravel the secrets of the Big Bang. Has it stopped working? Okay. What was... Yeah, this is a problem with this globe. I have to look up. And then the voice has to be louder, etc. Okay, we will manage. We want to push forward the frontiers of knowledge. Unravel the secrets of the Big Bang. What was matter like in the first moments of the universe, yeah? As you saw in the film. You cannot do this without developing new technologies for accelerators and for detectors, but also for information technology. And you might wonder, why do I have at the information technology here the web? Because some of the young people below 20, age of 20 or so, they might think that the web was born at the Big Bang. This is not true. The web was born 1989 at CERN, when our experiments became so international, so global, that we had to develop a software package to give information reliable, immediately, and all over the world to everybody who had the permission to access it. That was the birth of the web. And it has changed our world. Yeah? Today we have the grid computing, or in the private sector, the cloud computing, and of course we spin out to medicine in diagnosis and therapy. We cannot do it without training scientists and engineers of tomorrow. And if you build such a huge experiment, you need a lot of engineers, and you need a lot of engineers in different domains. So we are a fantastic training ground for scientists and engineers. And finally, we unite people from different countries and different cultures. This is a picture, for example, of the summer students coming for 2 months to CERN. We can house 250 summer students. We have more than 3,000 applications. And at CERN, as you already heard in the film, around 100 nationalities are registered. So we have people from around 100 nationalities working at CERN. So what do we want to do? We want to address one of the scientific challenge today to understand the first moments of our universe after the Big Bang. And you saw it in the film. From the Big Bang to today, the universe developed over 13.7 billion years, and it expanded from a tremendously hot spot up to 10 to the 28 centimeters. Now, who knows who can imagine what 10 to the 28 centimeters are? I cannot. Maybe it helps you if I give you an example. If you replace the centimeters by dollars, you have roughly the square of the American deficit. Actually, it doesn't help me very much. It only helps me to understand that the American deficit is pretty high. And one thing you have seen also in the film, around 400,000 years after the Big Bang, the universe became transparent. And this is what you can see with satellite, with space-based telescopes today. You get as close as 400,000 years to the Big Bang with space-based telescopes looking into light. We get much, much closer. I have it here again on the ruler. From the Big Bang to today, 10 to the 28 centimeters. This is difficult to imagine the large sizes. It is equally difficult to imagine the small sizes. Yeah? As from a certain moment on, the imagination stops. It's essentially zero, for me at least. So what we can imagine, of course, is the human dimension. And I have put here the young Rutherford in, because with Rutherford, 101 years ago, essentially, nuclear and particle physics started. So how can we look now into the history of the universe? We can do it either with telescopes, space-based or ground-based or space-based telescopes. We can look into the history of the universe. And as I just said, you get roughly like as close as 400,000 years to the beginning of the universe. If you do it with neutrinos, you get it down to 1 second close to the Big Bang. You can do it differently. You can go to the small sizes, go close to the Big Bang on this side, and you use the Large Hadron Collider. And the Large Hadron Collider is nothing else since a super microscope. And we come not as close as 400,000 years to the Big Bang, not as close as 1 second. We come as close as 1/millionth of a millionth of a second. Pretty close. In human dimensions, this is very, very close. In the dimensions, in the time dimensions of the universe, this is very far away still from the Big Bang, because everything has developed during that time. So how do you do it with accelerators? Well, the role of accelerators you can see here. You need high energy to resolve the inner structure of matter, because the wavelengths, that means the distance you can resolve, gets smaller and smaller the higher the energy. So you can resolve the inner structure of matter. Or with higher energy, according to Einstein, you can produce new particles. And at accelerators, you can produce these particles with very high statistics, what we call high luminosity, so you can do precision measurements. High energy and high statistics are the key issues for the accelerators. And don't worry, there are already 2 equations here. I think I have only 1 more. So how do we accelerate the particles? Well, assume you have a battery of 1 volt and you have the proton, the nucleus of the hydrogen atom, and you let it run through a space of this through this 1 volt from the plus pole to the minus pole, and then it acquires an energy of 1 electron volt, where the E stands for the charge of the proton because it's 1. Now at the LHC we have an energy of 2 times 7 TeV, where 1 TeV is 1000 GeV, is a 1 with 12 zeros electron volt. So you need for the LHC 2 times 7,000 billion batteries, which would be 14 batteries per star in the Andromeda galaxy. Well, we do it slightly differently. But this gives you an idea how much energy you have to put in for the acceleration of these particles. But with such an acceleration of the particles, you get, as I said, as close as indicated here, or 1/1,000,000th of a millionth of a second to the Big Bang. And the nice thing is here, if you study the physics laws of the first moments after the Big Bang, you have a fantastic symbiosis between particle physics on the small scale, astrophysics on the large scale, and the cosmology. And this is what I think brings the young people into science. These big questions, cosmology, particle physics, astrophysics, and the beginning of the universe. Now, what have we learned up to now with our previous microscopes or super microscopes? Well, Rutherford, I told you, has shown that the atom is essentially empty. That means you are essentially all empty, huh? Okay. It consists out of the nuclei and the electrons. Now, the nuclei consists in turn out of protons and neutrons, and these protons and neutrons consist out of the quarks and the gluons. And the atomos of today is no longer this atom, are these constituents of matter, the quarks, the gluons, and the electrons, the leptons. These are what we call the point-like particles. We have not seen the substructure of these particles. Let's have a look what we have learned about this over the past years. Well, matter consists out of matter particles. Two quarks, the up and down quark, they make the protons and the neutrons, and in turn, they make the nuclei of the atoms. And then we have the electron, which makes then the atoms, and its neutrino, its neutral counterpart. And the masses are indicated here. So the neutrino has a tiny, tiny mass. The electron has a small mass. Up and down quark has a slightly bigger mass. And that's all we need. That's all we need to describe us. Yeah? We all consist out of these up and down quarks and the electrons. All of us, including me. And the chairs you are sitting on, etc. But you see there's a lot of space. Now nature has decided that's not enough. Nature has decided to make a second family, exactly the same family. Charm and strange, two new quarks. The muon, the heavy brother of the electron, and the muon neutrino, the heavier sister of the electron neutrino. And the only difference between these two families is the mass of the different particles. So each particle here has a much, much higher mass than its brother or sister in the first family. Otherwise, they are all the same. Their properties are the same. It's just the mass. And then nature has decided to take a third family. And now you can well imagine what happens. These masses are even much, much higher. Yeah? The top quark here, the top quark here is as massive as a gold atom. It is as massive as a gold atom, but it's a point-like particle. We don't know of any substructure of this particle. So we have these three families which are only different in their masses, and for us, we only need the first family. In addition, of course, to these three families, we have for all these particles their corresponding antiparticles, the famous word antimatter. Now, particles and antiparticles are always created in pairs. According to Einstein again, you can transform energy to mass. You have energy, and then you get mass out, but always particle and antiparticle together. And they can also annihilate each other. That means you get mass back to energy when you meet, when matter meets, or particle meets antiparticle. And this is how it happened in the universe. Yeah? Each time matter and antimatter met, they annihilated and it went into energy. So if the properties of matter and antimatter would all be the same, we would not be here. because everything would be annihilated, because at the Big Bang, matter and antimatter were produced in equal quantities. However, nature has introduced a small asymmetry between matter and antimatter. 1 part in 10 billion more matter than antimatter. And this 1 part in 10 billion is sitting here. That's us. We are the leftover from this 1 part in 10 billion. But we don't know how nature has done that. We know a few conditions, but we don't know all of the conditions, how matter has done it. However, what we know is that there's no sign of antimatter in the universe. And one of the jobs of the LHC will be to find out how this came all about. Okay, so matter, stars, living organisms, everything consists out of 3 families of quarks and leptons. Matter around us, only one of the 3 families, as I told you, there's only one of the 3 families is needed for us. However, at high energies, matter is becoming democratic. All 3 families were present. So if we go at high energy, study matter at high energy, we get knowledge about the early universe. Now, between these matter particles, there are 4 forces acting. The strong force, which acts on the quarks, which holds the nuclei together. The weak force, which acts on all the particles, which is responsible, for example, for the reactions in the sun. The electromagnetic force acts on electric charge and therefore makes the atom neutral. And the gravitation acts on mass and energy. These 4 forces act between the different particles, and there are 40 orders of magnitude difference in strength between the strong force and the gravitation. 40 orders of magnitude difference in strength. The strong force is the strongest one. This one is the weakest one. However, this is for our energy range. So 4 fundamental forces act between the matter particles, and they act through the exchange of force particles. The gluons for the strong interaction, W and Z for weak interaction, photons for electromagnetic, and graviton for the gravitation. And within our energy regime, the respective strengths of the forces is very, very different, 40 orders of magnitude. However, at the high energies, all forces have been of same strength. The question is, was there only one force at the beginning of the universe? So if we study the forces at the high energies, we get knowledge about the early universe again. So we are doing that. So what have we learned over the last 50 years? I call it the discovery of the Standard Model. And it took us more than 4 decades, nearly 50 years. The physical world is composed of quarks and leptons interacting via these force carriers. And this is the periodic system of the microcosm. 3 families of 2 quarks, 2 leptons each, and the force carriers. And isn't that fantastic? This is such a small periodic system. So easy. Particle physics is much easier than chemistry. Yeah? The periodic system of the elements is much bigger. The last entries were 1995 and the year 2000 for the top quark and the tau neutrino. This is the static model of the microcosm, the Standard Model. However, you need a mathematical formalism to describe the interaction between the particles. And this is now the Standard Model of particle physics. It's a mathematical formalism which describes all interactions mediated through the weak, the electromagnetic, and the strong forces. And we have tested this model, its predictions, with very, very high precision. We have validated it down to distances 10 to the minus 18 meters or up to energies of 100 GeV. And up to now, this thing is withstanding all these tests. It's fantastic. It's a fantastic achievement. Yeah? On the other hand, it's absolutely frustrating, because there's one piece missing within the Standard Model, which is absolutely vital. And that's the question, what is the origin of mass of elementary particles? Because the mathematical formalism for the Standard Model originally was only valid for massless particles. Now I have shown you they are all massive, or most of them are massive. And the guys who developed the mathematical formalism, of course, they knew it. But one of them said, yes, I know it's only valid for massless particles, but let's forget it. And it was correct that they forgot it. Because then a few years later, there was a possible solution. Because you can define the mass as a property of the particles with a certain energy E to move, and that's my last equation, with a velocity which is not equal to the velocity of light. If the mass is 0, then the velocity is equal to the velocity, then this equation is 1, so the velocity is the velocity of light. The more massive the particle, the slower it is moving. That means the higher the mass, the lower the velocity once the particle has the same energy. So how to solve that? Well, you can introduce a scalar field. Scalar field is a field which is everywhere without a pronounced direction. So everywhere the same in space. And the particles acquire mass through interaction with this field. And the self-interaction of this field gives the Higgs particle, which is named after the physicist Peter Higgs. This sounds very difficult. It's very easy. This is the Higgs field. This is a party or a cocktail party of journalists after the cold buffet has been emptied, because otherwise they would all be at the cold buffet, like physicists. Now they are equally distributed in the whole room, in the room. There's a door here and there's a door there. And then I want to go in and go through this room with a velocity of light. The journalists don't know me. I go through without any interaction with the journalists. My velocity is a velocity of light. I have no mass. I'm massless. But now somebody comes in who is a bit known to the journalists, and they cluster around him. So that person acquires mass through the interaction with the field of the journalists. Like a particle acquires mass through the interaction with this Higgs field. And the better known this person, the more massive this person gets. So it depends on the knowledge of the journalist with respect to that person, how massive that person becomes. This is how a particle acquires mass. Now, how can I imagine now the self-interaction? Well, suppose I open the door and I whisper a rumor into the room. The journalists are curious. What did he say? That's the Higgs boson. That's the self-interaction of the field. And the Higgs boson is produced, decays, because people are clustering differently. So this is the mechanism how elementary particles acquire their mass. Again, I think pretty easy, isn't it? So, the Higgs particle is the last missing cornerstone within the Standard Model. And we know everything about it. We know all its properties. The only thing we don't know is if it exists at all. It's a slight problem. But there are many more key questions of particle physics open still. The first one is the origin of mass. Then the question, can we unify the forces in our theory? Because we know that at the high scale, at the Big Bang, the forces should have been the same. We cannot do that within the Standard Model. That's the dashed lines. We can do it if we introduce some new theory. We don't know how it happened, what happened to antimatter. We don't know that yet. We don't know how many space or time dimensions do we live. Do we really live only in 3 space dimensions? We don't know. What is dark matter? What is dark energy? All these questions are not addressed by the Standard Model. The LHC, however, will address most of these questions. in particular the one of dark matter and dark energy. Because the standard model, which we developed over 40, 50 years, only describes roughly 5% of the universe, the visible universe, us. 95% of the universe are dark. 1/4 is dark matter. It clumps like normal matter. And 3/4 of the universe is dark energy, which drives the universe apart. So dark matter and dark energy are working against each other. We know very little about dark matter. We know even less about dark energy. But my hope is really that with a Large Hadron Collider, we are now entering the dark universe. The Large Hadron Collider is one of the largest scientific instruments ever built, 27 kilometers of circumference, more than 10,000 people involved in design, construction, and now exploitation. It collides protons to reproduce conditions at the birth of the universe 40 million times a second. And this is the 27 kilometers ring. It's 100 meters roughly underneath the surface. We have 2 tubes in which we have the protons running in packets. I will come back to that. And at certain points, we bring them to the collision. So this is a magnet of the LHC. We have 1,200 of these magnets in the 27-kilometer ring. We have one position where it can go down. And then it's transported around the site until it reaches its position. Here, this magnet here has reached its position. Then it's put into place, adjusted, and then, of course, you have to connect. You have to weld these high current connectors here, and we have 10,000 of these high current connectors. And then when everything like this is done, it looks like this, and this is how I want to see it, because then we can take data. Then we can run the machine. It is one of the coldest places in the universe, because it's run at a temperature of minus 271 Celsius, or 1.9 Kelvin above absolute zero. The LHC is colder than outer space because outer space is at 2.7 Kelvin. So we have the largest refrigerator on Earth. At the same time, it is one of the hottest places in the galaxy, because at the collision of these 2 protons, energy densities, temperatures are produced much, much hotter than in the inner of the sun. If you take the 2 protons and you collide the 2 protons, the energy is like a mosquito in full flight hitting another mosquito in full flight. I don't think you get very close to the Big Bang with this. What counts here is that the protons have a tiny, tiny area only. So it's not the energy, it's the energy divided by the area of the proton. That means the energy density. And that brings you very close to the Big Bang, this 1/1,000,000th of a millionth of a second. So the design energy, I compared it already with the batteries. 7 plus 7 equals 14 TeV. We have 2,800 on 2,800 proton bunches, packets of protons, separated by 7.5 meters. And per bunch, per packet, we have 100 billion protons in this packet. And then we squeeze this packet, and then we collide it. And then we have many collisions, many interactions per crossing of a packet. Today we are at slightly lower rate. We are only with 1,400 on 1,400 bunches, so 20 megahertz crossing rate. And 4 on 4 TeV, that makes 8 TeV. But the luminosity, the collision rate per second is nearly already as we want to have it, 6.5 10 to the 33 instead of 10 to the 34. If you scale with energy, then we are already now beyond the design luminosity, beyond the design number of crossings per unit time. So we have per second 10 to the 9 proton-proton interactions, 1 billion proton interactions. In each collision of a packet, more than 1,000 charged particles produced, which of course is an enormous challenge for the detectors and for the data collection, for the data storage, and for the data analysis. And these are the detectors. We have 4 positions where we have 4 big experiments, 4 big detectors, 2 omnipurpose experiments. Atlas is the one where the Canadian physicists are very strongly involved, as you heard from Rob. And Atlas and CMS, the omnipurpose experiments, they are supposed to measure all the interesting collisions which happen. LHCb is a special experiment that looks at the question, why are we at all here? That's a question of this difference between matter and antimatter. That's a speciality of LHCb. And ALICE is a dedicated experiment to measure collisions of heavy ions, because we are not only colliding protons, we are also colliding lead ions 1 month per year. Now let's look at this detector here. It's certainly one of the largest and most complex detectors. It looks today completely different because it's filled now with detector elements. It's completely full. But to give you an idea, this is the size of an average technician. Okay, a few people got the joke. Okay, this is roughly 25 times 25 times 40 cubic meters. And in the whole volume of this experiment, we measure the trajectories of the particles coming out with an accuracy roughly of the diameter of the human hair. So this is fantastic. Now, would you agree with me that this also looks like engineering art? Yes? Yes? Okay. So what's that? You see these red stripes here. You see the 8-fold symmetry, everything here. Compare it to Atlas. Fantastic. It's nearly the same, slightly different. It's a stage design for an opera, the opera of Hector Berlioz, which was played first in Valencia in Spain and then at a few other places in Europe. And you see, science and arts belong together. Yeah? Artists are inspired by scientists and vice versa. And this is why we have introduced at CERN a new program, Artists in Residence. So we are not only colliding particles, we are also colliding artists with scientists. Actually, this is a very interesting experiment. We started it this year, so we have to see how. But this is very interesting. Okay, now, what are the basic processes at the LHC? Well, you have the 2 protons, and the 2 protons are not elementary particles. They are composite particles out of gluons and quarks, and you never know which gluon or which quark from which proton hits the other one. So you have many, many different reactions, for example, quarks and quarks, and hitting a quark, and then again 2 quarks can come out and form a jet, to each a jet of particles. And if you look now in the Atlas detector here, if you roll it out, you see very nicely these 2 jets of particles here in energy. So you see the 2 very focused streams of energy in the detector. This is an indication that there were 2 quarks produced. And this is what I would call the bread and butter, the normal physics with which you start. Of course, we are looking for rare processes for new physics. And one of it could be that, for example, 2 gluons fuse, and then you have the Higgs particle, and the Higgs particle then decays again. And that would very nicely show up here in this experiment, for example, in 4 tracks as decay products of the W or the Z. This would be an indication of the Higgs particle or an indication of new physics. The problem is, this is the total production rate here at the LHC. And there are many, many orders of magnitude below is the new physics. So you need many, many collisions and a very sophisticated algorithm. You have to select 1 out of much more than 10 billion collisions in order to find the interesting events. So many orders of magnitude are in between here. And what you have to do is you accumulate and accumulate collisions. This is on the horizontal scale. Over the past 2 years, we have accumulated more and more collisions. Today, we are here. And when you accumulate more and more collisions, then you can do more and more physics. You can start here with the 2 quarks, for example, and then go into the standard candles of the standard model, the W's, the Z's, the top quark, and you look into all of these reactions and look, do they agree with the standard model? Of course, the first thing you have to do at the high energy, you have to prove that you can identify the physics which you know from the lower energy before you can claim new physics. You have to prove that you understand the old physics, so to speak. And this is on one transparency now here. Start with a very high production rate, going down to a very low one, like for two sets to be produced. And you see the dots are the data, and the lines are the theory from the standard model. And you see everything agrees perfectly well, to my taste, even too perfectly well, between data and prediction of the standard model. So the standard model has really been rediscovered at the high energy. So there was excellent performance in 2010 and 2011. We have accumulated a large amount of data. We have rediscovered the standard model, and these are our standard candles which we have seen and confirmed at the high energy. That means the experiments have completed their journey through the standard model. We have rediscovered it, as I said, and they have started to take us now into new territory. And what is a new territory? Well, Newton's, in inverted commas, unfinished business. What is mass? What is the mechanism to give mass to fundamental particles? Why is there no more antimatter? What was matter like within the first moments of the universe life? And the little embarrassment, what is 96% of the universe made of? Let's start now and look into that. Look first into why is there no more antimatter? And now, Roger, are you still awake? Roger, are you still awake?
Yes.
Ah, okay. I know where he was sitting, so. This is a penguin because what they are looking here in this experiment LHCb is for the difference between matter and antimatter, and they look, for example, through these penguin diagrams to it. Now this looks very complicated. Let me guide you through. Look at these blue curves here, the 2 top ones. Here you have the matter particle decaying into 2 particles, and here you have the antimatter particle decaying into the same particles as the matter particle. And you see these ones are the red ones. And you see immediately by eye that the matter particle decays more often into these particles than the antimatter particle. So there is a difference between antimatter and matter. Now you see the blue one has a shoulder here in both diagrams. Now you look into a different particle which also decays into these 2 particles. This is the same meson but has a strange quark in it. And this is a green one. And you see here the green one, the matter particle, decays more often into these 2 particles than the antimatter, no, less often than the antimatter particle. So matter decays less often into these 2 in this case, and decays more often in these 2 particles in this case. So this is how you look for asymmetries between matter and antimatter. Now these tiny asymmetries which they see here are still within the standard model. So there's nothing new. The present status is there's excellent agreement with the standard model in this case. However, they have now seen for the first time possible evidence for new effects in other channels which are more complicated to describe, just to show you that there might be something beyond the standard model at LHCb already now. But it is only 3 sigma, and one has to be careful. But you can also study antimatter not at the LHC. You can look at CERN also and compare hydrogen with antihydrogen. Does it have the same behavior? And you can compare the proton with the antiproton. And you can measure the mass of the proton and the mass of the antiproton. Is there a difference? And the present result, there is no difference within 10 orders of magnitude. So if you take 2 elephants, the difference is less than 1 dust grain. So the present status, there's excellent agreement with what we know between matter and antimatter and what is predicted by the standard model. So we still have to search a lot, and it will take many, many years to shed some more light on that. Okay, now let's look on the next one. What is mass? And what is 96% of the universe made of? What is the dark universe made of? And I hope you are now ready, together with me, to enter the dark universe. Let's first look at dark matter. Now, dark matter, I told you, is roughly 25%, whereas visible matter is roughly 5%. So it's clear that dark matter must have shaped stars and galaxies in the night sky, which we see in the night sky, much more than visible matter. So that will be told to us by astronomy and astrophysics. But only at particle accelerators you can produce dark matter candidates in the laboratory, and then you can investigate it and understand exactly what it is. Is it composed of a single kind of particle? Or is it more rich and more varied as a visible world? We don't know. But the LHC might be the perfect machine to study dark matter. One of the best candidates for dark matter is supersymmetry. Supersymmetry unifies matter with forces. For each particle of the standard model, you have a supersymmetric pattern of opposite statistics. So you have, a, so to speak, a shadow world. Well, I often get confronted with a question, with a remark then, well, if the physicists don't know how to explain things, they just double the number of particles, and they can explain everything again. But don't forget, a bit more than 80 years ago, Paul Dirac has introduced antimatter, which we dealt with before. It's only 80 years, a bit more than 80 years. And with the introduction of antimatter, he has, with one equation, doubled the number of particles. And since 40 years, we are using it in the hospital. PET, positron emission tomography, the positron is the antiparticle of the electron. I'm not saying that we will use in 40 years supersymmetry in the hospital, but just to give you an example or a feeling what can come out of such basic research. Now, supersymmetry allows to unify the forces, as I showed here, and it provides a dark matter candidate because the lightest supersymmetric particle should be stable in many of the models. So, here you have the standard model. Again, the 3 families, the force particles and also the Higgs particle. And then for each of these, you get a supersymmetric particle, again, 3 families, and the force particles. Now at the LHC, you can produce the supersymmetric particles if they exist. And then they would decay in a lower mass supersymmetric particle plus a normal particle, a standard model particle, again in a lower supersymmetric and a lower and another standard model particle, until the supersymmetric particle, the lowest supersymmetric particle, doesn't have a partner to decay into, and it can escape the detector. So the trick is to look for missing energy, because these particles would escape the detector, you would miss energy, you would miss momentum. And this is the way you would look for supersymmetry. And now comes a very complicated plot, which is just to show you, these are all different models of supersymmetry. So supersymmetry has a vast parameter space, many, many models, and you see the experiments were looking for particles in these different models of this, and here's a mass scale of these particles. And for many of the models, we are already at the 1 TeV mass scale, which means within the constraint models which have few parameters, the air is getting thin because We can exclude these particles. However, this is only true for the constrained models. We have the supersymmetric models which are not constrained, they are still very, very open. So the potential for the discovery of supersymmetry is sizable even at 7 or 8 TeV, which we are running now. However, for the theorists, it's becoming a bit more difficult now with ATLAS and CMS and LHCb killing some of the models, and some of the theorists have to think about other models now. So the LHC results should allow, with dedicated dark matter searches, first discoveries in the dark universe. However, around 75 or 3/4 of the universe is in some mysterious dark energy, which is evenly spread. And the challenge is to get first hints about the world of dark energy in the laboratory. And I haven't talked about the Higgs yet. The Higgs is different because all matter particles have spin and all force carriers have spin. But the Higgs is different. The Higgs particles are spin zero. They are scalars. They have no spin. They are neither force nor matter. The Higgs is just different compared to the other particles. And if we find it, if it exists, this would be the first fundamental scalar ever discovered. And I told you, dark energy is a scalar. It's evenly spread. The Higgs is also evenly spread. So both must be scalars. I'm not saying by no means that dark energy and Higgs is the same, but both are scalars. And if we can study the Higgs, then we could maybe find out some properties of scalars, or fundamental scalars, and maybe that could give some handle on dark energy. And the LHC, of course, can search for scalars and study for these with precision. Now, the search for the Higgs boson at the LHC has several problems. First of all, I showed you already this plot, the total production rate of particles, and many orders of magnitude below, there would be the production of the Higgs boson. And the Higgs boson would be produced and would decay immediately again, and it has several possibilities. Its picture, as seen in the detector, can be very different depending on the mass of the Higgs boson. You see how many decay possibilities this Higgs boson has in this mass range. So the problem, you have to imagine what you have to do. You have to search for a snowflake in a huge snowfall with photos. You make photographs of the huge snowfall, and you have to identify special snowflakes. This would be the Higgs. However, this snowfall, you take the picture in front of a snow field. Yeah? So the difference between the Higgs and the other reactions which you have is very tiny. So it needs a huge amount of data to look into all these different pictures, different decay possibilities. And here, don't look into in detail. What I want to show with this transparency is, you see the background, the snow field and the snowfall are the dots and the diagrams. And the special snowflake, the Higgs, are the red squares. And you see small red squares over big background of so the special snowflakes over the big background of the snow field, of the snowfall. This makes it so difficult to find the Higgs boson. However, the signature is striking. This is the decay, possible decay of a Higgs boson into two photons. You see the two high energy plots here, the two photons with high energy measured here. However, it could be either a Higgs or a background event. Again, so you need many of these in order to have a decisive answer. So the status of today, the standard model Higgs boson is excluded up to a mass of 600 GeV, except for this window here, 122.5 to 127.5 GeV. And the nice thing is that there are interesting or intriguing fluctuations inside this window around masses of 24 to 126 GeV. So 2012, we are running now very well. We have already nearly the same amount of statistics accumulated as last year. And already last year, I stuck out my neck and I said, the Shakespeare question of the Higgs boson will be answered end of this year, to be or not to be. And this is a key message here for the LHC and the Standard Model. Finding the Higgs will be a discovery. Excluding the Standard Model Higgs would also be a discovery, because it would be for the first time that we have found a big hole in the Standard Model. So either we close the Standard Model with a discovery of the Higgs, and then we describe 5% of our universe. Or we exclude the Higgs, and then we have to find something else, namely that which does then the job of the Higgs. But this is beyond the Standard Model. So both would be a discovery, because the LHC will clarify the mechanism by which elementary particles acquire mass. Now, at the moment, it looks, to my mind, very nicely like the first line. We will see. End of the year, we will know. Okay, so LHC results will allow to study the Higgs mechanism in detail and to reveal the character of the Higgs boson. This would be the first investigation of a scalar field and could be maybe the very first step to understanding dark energy. So the past decades saw 5% precision studies of 5% of our universe, the discovery of the Standard Model. The LHC delivers data very, very well. I think we are just at the beginning of exploring 95% of our universe. And I would say the future is bright in the dark universe. Thank you.
Thanks, Dr. Hoyer, for that wonderful talk. We'll just let him catch his breath. And we have 2 microphones that will be going around the audience. And if you have questions for Dr. Hoyer, please put up your hand or stand up, and we will attempt to find you, because you can't actually see a single thing when you're looking up into the audience. Now, let me warn you, if you are shorter than this, you get to ask your question first. All right? Students, children, if you have a question for Dr. Hoyer, you get first crack at it, and then your parents. Does anyone have their hand up? I can't see. Okay.
Is the doing anything interesting with
The question was, is the LHC doing anything interesting with gravity?
No, actually, it's, the strength is much too small at the moment.
In your opinion, personally, do you think we're going to find the Higgs or rule it out?
My opinion doesn't count. What counts is what nature gives us and what we will find, and I will not tell you my opinion.
Oh, yeah, so if we don't find the Higgs, what are the alternatives?
I guess you want to ask what are the alternatives?
Yes.
Oh, there are many, many different theories. You can have another force. You can have another sort of strong force. You can have composite particles, which called Technicolor, which could do the job. However, the one which is, all of these, of course, have to agree with what we have measured up to now. And this is for many of these other theories a bit difficult. So the one which is the most beautiful one, and therefore maybe the most believed one, or maybe the one which we believe now since many, many years more on it, is the Higgs mechanism. However, there is a variety of other models, of other possibilities which could do it. The problem is, with the Higgs boson, as I said at the beginning, we know all its properties. This is why we can predict when the number of collisions are sufficient, at what moment the number of collisions are sufficient. With the other models, we don't know the properties exactly, and therefore we cannot predict when we would fill the hole if the Higgs boson is not there.
We have a question on this side. On one of your supersymmetry slides, there was a line about connections to string theory. I was wondering how the supersymmetry theories imply string theory, or how they connect.
Well, many of the superstring or string theories need supersymmetry as a basic ingredient of their models, of their theories. That means many string theories, wouldn't exist anymore if we don't find supersymmetry.
William, is that you? Yes, you have mentioned that the MLHC has very high energies, such as approaching like 8 teleelectrovolts. Do you think there's a natural limit, that is an absolute limit of the energy we could get with using any technology?
It depends how much money you give me. Oh, excuse me. Excuse me, I'm really jet lagged now. In principle, not, because it just depends then on the size. But there is, of course, a certain limit of what size you would do. What you have to do is you have to develop new technologies, and we are working on new technologies to increase the acceleration per unit length. And if you in the LHC tunnel, there was LEP beforehand, E plus E minus machine, 200 GeV. Now we are going up to several TeV with a proton machine. So you can go on even on the same length with different particles, with different mechanisms of acceleration. And there are new concepts worked out for new particle accelerators. It depends on the length and the gradient which you have. So a natural limit is maybe the Earth circumference, which is, of course, foolish to do that. I would never dream of, it would be a nightmare. It would not be a dream. You would not do that. But I don't think there is, in principle, a natural limit.
Thank you.
We got one over here.
Yes, I noticed in your presentation that the four forces, it stated that at one time near the Big Bang, they were all perhaps one force. And my question is, there was a speculation that gravity, the force of gravity, weak force, create multiple dimensions or universe. Could you comment on that?
I mean, in principle, yes, if I would have understood the question that, yeah.
Yeah, in your lecture,
No, the first part was okay, the speculation part was not okay.
The speculation is what you want to know?
Yeah.
The dark force, the weak force of gravity, that is still the current speculation that weak force being the weakest of the three, that it indicates multi-universes or other universes, because bleeding out into the other universe.
Well, there are theories about multiverses, and there are also theories that only gravity can interact between the two. This is correct, yes.
But are there other models that would explain it besides that, or is that still the current thinking?
I need a theorist now. No, that's at least, you see, once you have theories, then you also have several opinions. And I think both exist. I mean, I'm not sure if one is the more the the more sound one.
Well, because you stated, or the lecture stated that near the beginning of the universe it was one force, perhaps.
Yeah. I mean,
so at that moment, would it be a possibility there would be a multi-universes connection?
I guess. I don't know. That's too much for me. I mean, for me, it is now 5 o'clock in the morning.
We'll take a few more questions. We have one over here from somebody meeting the height cut.
Do you want to ask a question?
There's one in the back. One way in the back.
I had a question about your analogy earlier on with the Higgs field would be a proven journalist. And you mentioned that particle moving through the Higgs field was like journalists clinging on to the mass.
It's essentially impossible to understand. Can the mic be a bit louder?
Okay. So, can you hang on to your question for just a second? We have a mic down here with a young person who's about to ask a question. Then we'll get the mic up to you. Okay, go ahead.
Is the universe expanding from a certain point?
I wish I would know. I wish I would know. You see, we have the theory of the expansion from a certain point. But I cannot imagine where this point was. But it must have been a certain tremendously hot, energetic point, yes. Does this answer your question roughly?
Answer your question? All right.
Okay, so I'll start over again. Earlier on, you made an analogy between the Higgs field and a room full of journalists. And a particle moving through the field was likened to journalists clinging on to give it its mass. And my question is, in this case, with particles moving through the field like this, and these things clinging onto it, does that reduce the density of the field over time as particles gain mass by moving through it?
No, my immediate answer would be no. No, because energy and mass is in that sense the same, and therefore the mass and energy density of the whole thing is the same. So that's constant. So the answer would be no.
Is there anyone else? I can't. Somebody with a mic? We got one over here, and then there's two people with their hands up over here, and then one there, couple over here, and then I think we're going to let Dr. Hoyer get some sleep.
Hi, Dr. Hoyer. Thank you for a wonderful talk. I'm not a scientist. I'm just a curious human being, and I had a few questions. As the LHC was built in recent times and we're trying to explore the questions of the beginning of the universe, I'm just curious about what type of safety has been done about the LHC and with our changing technology and engineering in recent times. Secondly, you said that we do a lot of proton collisions, but there was a short part where you mentioned there were also experiments on lead ions, and I was curious about that. And lastly, you mentioned that it's only been about 101 years since particle physics or Rutherford, and it sounds like we've solved so many questions in relativity to the expand of human existence. How long might it take to solve all these questions about the universe's beginnings as a guess? Just a few hundred years? It seems like we're going so fast.
Okay, that's a second talk. The last question first. Who defines that you know everything about the beginning of the universe. I mean, that's the first point. I mean, who is defining that? And then you can say when you have the end. So this is already difficult for me, because there will be always new questions open. I mean, this is what I personally find the beauty of research is you find something, you learn something, and you learn new questions to ask. So I don't dare to give any idea how long it will take to shed some more light on or coming close to understanding the much more about the early universe. We will hopefully solve, or at least partially solve, some of the questions, but there will be many more open, much more detailed questions. So it will take a long, long time. On the technology, the first question, when the whole project was started, the magnets which hold the particles on their trajectories were not existing. The technology for these magnets was not existing yet, so it had to be developed. So it takes many, many years of research and development, and then many years of building. And of course, in that course, you also develop the electronics and everything which you need in order to steer the beam, in order to make the beam safely go around. Because if something goes wrong, then you have to repair the machine, and that takes quite some time. I think that was your first question, and I forgot the middle question. Are the lead ions? What do you want to know about the lead ions? What the science we are doing with it? Well, if you collide, instead of 2 protons, 2 lead ions, which, if I'm not mistaken, have 82 protons, then you have a much, much higher density in the collision. You create a sort of hot, dense matter, which is most probably a sort of quark-gluon plasma. You create, no, you don't create. Creation is somebody else. You produce this state of matter which you can then investigate its properties. You can investigate what happens to particles which are inside that hot dense matter. Do they change their behavior, etc.? And these are the measurements they are doing in order to understand how, at the beginning of the universe, this hot dense matter, this quark-gluon plasma, was behaving. This is, in a nutshell, a longer talk.
So we have a couple of questions on this side. Oh, now we got so many more questions. Let's try to make each one quick. Yeah.
Good evening. I was wondering who pays for all this research?
You were wondering?
Who pays?
Who pays for all this research? Public money. This is basic research, and basic research is funded by public money. And our budget is comparable to the budget of a large university in the UK, for example. And at the LHC at the moment, there are, if I'm not mistaken, 3,000 students performing their PhD thesis. So it's like a university.
We have time. I know there's a million questions that people want to ask.
But I think at some stage we should also
one more.
Release the speaker.
Yeah. And one more question.
Yeah, I was just wondering, are there any plans at CERN to build, maybe in the future, a whole other project for another way of looking at this, or is the LHC it?
I mean, I would be a bad DG if we would not have other plans. Of course, yes. I mean, first of all, for the LHC, we have a 20 years plan. The LHC, we foresee running until roughly 2030. Then I think it has done its job. And we have several other projects in the drawer, which we could, in principle, do. However, it does not make sense to put any of these projects out before you don't know which direction the LHC tells you to go. You have to know that before. But you do, of course, R&D in order to be prepared for the future. Yes.
Well, let's thank Dr. Hoyer one more time for a fantastic talk.